Okay, class, today we're in section 1.2, sets of real numbers. Section 1.2, sets of real numbers. Okay, write down the title section and the title number, and let's get started with some notes.
Numbers come in all shapes and sizes. Let's take a look at some numbers and see if we can classify them by name. Before we look at our first example though, let's take a look at this chart. All the numbers here are real numbers. Rational numbers, irrational numbers, integers, and whole numbers. Okay. Now the real numbers are divided into two subsets: rational numbers and irrational numbers. Irrational numbers are numbers that cannot be written as fractions. Rational numbers, on the other hand, are numbers that can be written as fractions. Then we have our integers. Our integers they're like whole numbers, but they're positive and negative numbers. So you know whole numbers are only positive. And integers, now we introduce also the negative numbers as well. Whole numbers start from the number 0, then 1, 2, 3, 4, 5, and so on and so forth. Now, it's kind of weird that we have square root of 4 in there, but if you simplify square root of 4, square root of 4 is equal to 2. So as you can see, 2 is a whole number, and therefore square root of 4 is in the right place. Now, let's go ahead and look at our first example. We have negative square root of 7. Let's start here. Is negative square root of 7 a rational number? Well, first we need to ask ourselves, can we write it as a fraction? Well, 7 is not a perfect square, so since it's not a perfect square, negative square root of 7 cannot be written as a fraction. So I already know it's an irrational number. Irrational number. Okay. And also, since it does fall into our subset of numbers in here, it has to be a real number. Now let's go ahead and look at our second example. Square root of 25 over 5. Before we do this example though, we need to simplify. So let's write it in its most simplest form. Square root of 25 we know is 5. And we have our denominator 5. And if we simplify 5 over 5, we get 1. Now it's easier to figure out what kind of number 1 is, or what name applies to that number. Okay, so we know 1 is a whole number. But remember, we're really, just a reminder, we're really looking at the square root of 25 over 5. So I'll circle that. That's really the number we're looking at. This just helps us determine the name of that number. So we also know it's an integer. And now we have to figure out whether it's a rational number or irrational. Well, we already said, if you can see my work here, you can see it can be written as a fraction. So we know it's a rational number. And of course, has to be a real number. And finally, let's look at our last example. This is a challenging one. 0 and 6,667 10,000ths. Well, can we write that one as a fraction? If we can, then it'll be a rational number. Let's think about this. This decimal is a terminating decimal. Since it's a terminating decimal, I can write it as a fraction. But how? Well, if you just read it out loud, it's easier to see how we can write it as a fraction. So we already said that 0 and 6,667 10,000ths. So that number is 6,667 all over 10,000. 10,000ths. Well, there you have it. we can write the decimal as a fraction, therefore it has to be rational. Okay? And since we know it's rational, it cannot be irrational. And also, it's a real number since it falls into one of our subsets. And there you have it. Have fun classifying numbers. I'll see you next time.
Okay, so our essential question for today is, how can you describe relationships between sets of real numbers? Classifying real numbers. Biologists classify animals based on shared characteristics. A cardinal is an animal, a vertebrate, a bird, and a passerine. Animals, vertebrae, birds, passerines. You already know the set of rational numbers consists of whole numbers, integers, and fractions. The set of real numbers consists of the set of rational numbers and the set of irrational numbers. All right, now let's take another look at the chart that the young lady exposed you to a little bit earlier. You have real numbers, and real numbers are made up of rational numbers and irrational numbers. Rational numbers would include integers, and integers are positive and negative whole numbers. Whole numbers are positive numbers beginning with 0. Irrational numbers are any numbers that cannot be expressed as a rational number. So irrational numbers cannot be written as a fraction. Okay, let's take a look at example 1. Write all names that apply to each number. The square root of 5. The square root of 5 ends up being irrational and real. Now here's why. Anytime you do the square root of a number, if it is not a perfect square, then it is automatically irrational. If it is not a perfect square, it is automatically irrational. All right, now for those who may be confused on how the square root of 5 is not a perfect square, let's make sure you understand what a perfect square is. So what I did was I listed some numbers, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now of these numbers, which ones are perfect squares? Now what do we mean by perfect square? Perfect square means anytime a number can be multiplied by itself to give you that answer. All right, the first perfect square will be 1. Why? Because 1 times 1 will give you 1. All right, 1 times 1 is equal to 1. Is 2 a perfect square? No. What's the square root of 2? You got to figure that out. It's not a perfect square. What number times 2 will give you 2 if you multiply it against itself? There's no such number. The same thing for 3. What number, when you multiply it against itself, will give you 3? There's no such number. Now look at 4. What number, when you multiply it against itself, will give you 4? It'll be 2 times 2. 2 times 2 will give me 4. The square root of 5, what number, when you multiply it against itself, will give you 5? No such number. Therefore, 5 is irrational. Just like 2 is irrational and 3 is irrational. 4 is rational. 5 irrational. 6 would also be irrational. 7 irrational. 8 irrational. You cannot think of a number when you multiply it against itself, it would give you 8. And remember that, don't confuse 4 times 4 with 4 plus 4. It has to be through multiplication. Now look at 9. What number, when you multiply it against itself, will give you 9? That would be 3 times 3. So therefore 9 would be rational. Now according to our definition, a number such as a negative 17.84 is rational and real. Why? Because part of our definition is if a number is a terminating decimal, it is said to be rational. If a number is a terminating decimal, it is said to be rational. Now let's look at C, the square root of 81 over 9. Well, what's the square root of 81? That's going to be 9. You bring the 9 over because it's already 9. 9 divided by 9 is 1. Now once again, the square root of 81 is 9. 9 times 9 will give you 81. Because of that, that means this is going to be a whole number. 1 is a whole number. It's an integer. 1 is an integer. It's rational because it's on the rational side. And it's a real number because All numbers are real. Real are rational and irrational. Okay, next let's take a look at example 2. Understanding sets and subsets of real numbers. By understanding which sets are subsets of types of numbers, you can verify whether statements about the relationships between sets are true or false. Example 2. Tell whether the given statement is true or false. Explain your choice. A. All irrational numbers are real numbers. All irrational numbers are real numbers. True. Every irrational number is included in the set of real numbers. Irrational numbers are a subset of real numbers. Don't forget, real numbers can be rational or irrational. Refer back to your chart. So therefore, all irrational numbers are real numbers. All right, let's go to B. No rational numbers are whole numbers. No rational numbers are whole numbers. All right, once again, look at your chart and you'll find out that this is false. A whole number can be written as a fraction with a denominator of 1. So every whole number is included in the set of rational numbers. Whole numbers are a subset of rational numbers. All right, now let's take a look at example 3. Identifying sets for real-world problem situations. Real numbers can be used to represent real-world quantities. Highways have posted speed limit signs that are represented by natural numbers such as 55 miles per hour. Integers appear on thermometers. Rational numbers are used in many daily activities, including cooking. For example, ingredients in a recipe are often given in fractional amounts, such as 2/3 cups of flour. Okay, a quick definition did it not give you based on this paragraph. All right, natural numbers are counting numbers. They begin with 1, 1, 2, 3, 4. A way to think of natural numbers is that they're whole numbers, except they begin with the number 1. Whole numbers begin with 0. So whole numbers would be 0, 1, 2, 3, 4, etc. Natural numbers would be 1, 2, 3, 4. And of course, natural numbers would be rational numbers, which are part of real numbers. Okay, example 3. Identify the set of numbers that best describe each situation. Explain your choice. A. The number of people wearing glasses in a room. The set of whole numbers best describes the situation. The number of people wearing glasses may be 0 or a counting number. So in other words, it can be 0 or greater. It won't be negative, so therefore it won't be an integer, and it won't be like a fraction or a decimal, because there's no such thing as a half set of glasses or people. All right, B. The circumference of a flying disc has a diameter of 8, 9, 10, 11, or 14 inches. The set of irrational numbers best describes this situation. Each circumference will be a product of pi, and the diameter and any multiple of pi is irrational. So remember that now, any multiple of pi would be irrational. So in other words, if you multiply a number by pi, it would make that number irrational because pi itself is irrational.